Justin Flint here. Have you ever been performing surgery on your grape when your sweaty palms cause a slip of the knife and you stab your grape?
Oh no!
Does Aunt Becky never pull her weight when making the fruit salad for the cross-country family reunion? Are you tired of having to send an edible arrangement as a lousy excuse for not wanting to spend time with your family? Well, no more. We have a solution for you. A telesurgery robot to perform surgery on your grape. This telesurgery robot will ensure that a jerk of the knife never ruins your fruit salad again. For the low, low price of 3 payments of $1 million. That's right, you can prevent the eventual death and bleed out of your grape for 3 easy payments of $1 million. But if you call right now, we will slash a payment off that price. That's right, you can ensure another family barbecue fruit salad is never ruined by Aunt Becky's sweaty palms.
Telesurgery robots have become invaluable tools for assisting surgeons all over the country and the world in performing difficult surgeries with accuracy and precision from almost any place on Earth. While telesurgery robots are extremely complex and highly integrated systems, we can model them quite simply in reference to how the output angle is changed due to an input voltage. This plant, as you can see behind me, can be used to represent the telesurgery robot to design a control system and perform feedback analysis. The output angle of the motor sets the angle of the surgical device controlling the motion. The most important metrics for this system are low overshoot and the smallest amount of steady-state error. These are important for obvious reasons. You do not want to overshoot the position of surgery when beginning and cause a larger fissure. Nor do you want to think you are performing surgery on one part of the body and find out due to error you missed the needed area. However, as we can see in the step response behind me, our plant inherently has some overshoot associated with it, despite having no steady-state error. Assume that the typical constants relating to the motor are as follows. The resistance is equal to 0.1, the inductance is 0.01, KT is 1, and KE is 1. For our final system, we want the system to be very precise. Thus, in order to minimize the overshoot, zeta should approach 1 using a PD controller, while the inherent integrator of the system will set the steady-state error to 0 for a unit step input. There is some freedom in the value of omega because the rise time and settling time are not as important in the final considerations of the system, and this value of omega will be determined by choosing a reasonable rise time for the system. The following shows that the system is stable without a controller for low gain. And here, you can see the final BIBO stable closed loop design. By implementing a PD controller with 1.222 for KP and 1.342 for KD, we were able to show in our Simulink model that a unit step response will have approximately no overshoot, meeting the primary objective of our controller. The Simulink model also shows that we have 0 steady-state error, meeting the other main objective of the controller.
Do you have a step response for the plant?
Why, yes we do. The step response with the PD controller shows a rise time that is under 2 seconds with no overshoot or steady-state error. As you can see previously, there was significant overshoot with peak at 1.15 and total overshoot was 11.5%. Not what you want to see from an operating tool.
Since most surgeries are performed in a hospital setting, are you not worried about the plant being disturbed by an outside source?
Correct. Since this robot will be used in a hospital, it is unlikely it will be disturbed by a physical outside disturbance. There is a small and unlikely possibility that the plant could be disturbed by electrical interference.
What reference inputs can the plant follow?
The plant will only see a step response reference input, moving the reference immediately from the original angle to the new desired angle.
So are the dynamics going to be slow for the telesurgery robot?
Yes, somewhat. The plant dynamics for the telesurgery robot are going to be less than 3 seconds, which is not particularly fast or slow. This value is reasonable for the rise time of the system because rise time and settling time are far less important metrics to the system than minimizing steady-state error and overshoot of the system. Who wants to be under the knife and have the knife go in just a little too far?
Not me. So the desired specifications to acknowledge are percent overshoot and steady-state error. And rise time?
Yes. While we are most concerned with overshoot, we do want a reasonable rise time to ensure a quick response from the surgeon to the device. It is also important that the steady-state error be 0 to ensure the incisions are in the correct position at the correct length. Like previously stated, we are not worried about disturbances due to the highly regulated nature of hospitals. Therefore, we are only worried about controlling input from a unit step and not a unit.
How do you decide on the type of controller?
While we iterated through several types of controllers, we chose to use the PD controller because of its ability to reduce the overshoot and lower the rise time to adjust movements between incisions. The original overshoot was 14.6%, while the overshoot with the controller is 0.272%. Original rise time was 1.61 seconds, while with the PD controller it has been reduced to 1.23 seconds.
So did you just eyeball the step response of the system and decide that these are reasonable values?
Of course not! There were several tools available in MATLAB in order to accomplish these goals, and we chose to take advantage of two in order to check our results. First, the dynamics were tested using the SISO tool, which allows you to enter a transfer function and then change the dynamics of the system by either adjusting the gain of the Bode plot or adding poles and zeros to the root locus. Once desired results were developed using SISO tool, these results were compared to results using the simulated feedback tools.
Fascinating. So how does SISO 2 help you choose proper values for your controller?
Increasing the gain will decrease the rise time of the system, but will simultaneously increase the overshoot of the system. To account for this overshoot, we can add a zero near the crossover frequency, which is our derivative controller, in order to decrease the overshoot of the system almost to zero.
Okay, so that's cool. What else can you tell me about the response of the system?
Sure, let's take a look at the Bode plot of the system with our new controller. We see in our Bode plot the integrator in the low frequency response, and we notice that the system has a low bandwidth, which is good for minimizing response from unwanted frequencies. We see in the root locus diagram behind me that the system is actually stable for all values of gain once we add the proportional controller, and that additionally no poles of the system become dominant regardless of the gain.
Okay, so your system is stable for the chosen conditions. Can you elaborate on the robustness of your system?
Yes, thank you for asking. As can be seen behind me, in the Nyquist plot created using our PD controller, we can see that this system is actually stable for infinite gains, which supports our results from the root locus above. This means increasing the gain will expand the graph outward from the origin by multiplying each location and stretching the Nyquist plot. However, since the Nyquist plot goes to zero at the origin without a loop, increasing the gain will never make the system unstable. However, our system is not infinitely robust against time delay, as can be seen with the phase margin of approximately 80 degrees. The resulting phase margin of the system leads us to believe that the system can handle approximately 0.97 seconds of delay without going unstable. Because we are working with motors which experience delay less than 0.01 seconds, we further believe that the system is sufficiently robust to inputs from time delay.
Thank you for your time today. Our discussion has stemmed from interest in designing a feedback control system for telesurgical procedures, which we see as advantageous because of the robust precision of arm movements, as well as the ability to control such a device from long distances, capabilities which would be useful for experienced surgeons performing complex operations from different corners of the country or even the world.
We predicted that the initial dynamics of our plant design would be long-term stable, but we saw disadvantages of the plant with the rise time and especially with the overshoot of the system. Because we didn't want overshoot in our system, leading to unexpected or undesired surgical incisions, we decided to add a PD controller to our system, simultaneously allowing us to decrease the rise time of the circuit while still reducing the overshoot to approximately zero.
This design will allow surgeons to perform surgeries at a similar pace to hands-on procedures, while simultaneously allowing more precise movements with no long-term error resulting. With this design, we can hope for surgical operations which are more precise, while still allowing surgeons to perform complex operations all over the country without additional travel time.
Catch us next time when we discuss the advantages of using a feedback control system in designing autonomous vehicles.
Cut. Sort of. Not good enough.